In this example, we're given the set S, which is equal to V1, V2, V3, and V4. V1, you may recognize, as well as another friend from a previous example, but we're going to extend our bases, or our vectors here, to include two more in R4. Okay? So we have four-dimensional vectors, and what we're going to look at then is try to construct an orthonormal basis. Well, we're not going to normalize them yet. We're going to make an orthogonal basis, and eventually we'll make it an orthonormal basis. So to do this, then we need to take each of these vectors, and we're going to utilize the Gram-Schmidt process to orthogonalize them first, and then orthonormalize them. Okay, so according to the process, then we're going to set u1 equal to v1. So we're just going to take our first vector, which is our v1 here, and we're going to set that equal to v1. Okay, then the next step is very much like the previous example we saw. Um, we're going to we're going to look at the parallel and perpendicular components of this vector, and we're looking at the projection. So the Gram-Schmidt process says, okay, then you take your v2, the second vector, in your basis, and you subtract off of it any components that are not perpendicular to it. So you're subtracting off the parallel components to it. And to do this, then you're going to subtract off the vector, the inner product of u1, the one that you just found, and v2 divided by the norm of u1. Okay. And then that's also going to be in the direction of u1. Okay. So this is going to be the second vector that we're going to compute. We'll also do the calculations using technology. I'm just showing you the scheme that we're utilizing here. Okay, and then so for the next one, it's going to be very similar, but now you have uh, two things to worry about, two vectors and two orthogonal directions to be concerned with. So you're going to take V3 then and subtract off the inner product of U1 and V3, and then also going to divide by the norm of u1 along the u1 direction. Okay, and then you're going to subtract off the inner product of u2 and v3. That's a v divided by the inner product of u2 along the u2 direction. Okay, and so that will give you then the vector u3, and finally u4 is going to be v4 minus. Can you guess the pattern yet? Yeah, you got it. U1 and V4. Yeah, that looks more like a V. U1 and U1. The norm of that squared along U1 minus U2. Good. V4 over U2, U2. And then this is going to be along the U2 direction. And then finally, we have the parallel component we need to subtract off from the last vector that we just re-instructed, which was v3. So we have u3, sorry, I said v3 that we constructed. I meant u3 that we were constructing. That's a three. That looks weird. Oh well. Along u3. Okay. All right. So this is the vector that we're going to be working with here. So we're going to switch over to technology to finalize the calculations and arrive at our desired orthogonal basis. So we're using a different software because GeoGebra does not handle four-dimensional vectors. So we're going to use Maxima, which is a free computer algebra system that you can download from the internet. So here, what I'm defining is the four. This kind of jumped all over the place. So here I'm defining the four original matrices, four original vectors in our space or our set S. So this is just the notation for it. So you have to define the matrix, and then you have a single element along this. So this creates the 4x1 matrices or vectors, if you will, for V1, V2, V3, and V4. Okay, which you can see here. That's what it outputs. That's what we were looking for. Okay. Once I do that, then I set up the first two steps. So here is of the Gram-Schmidt process. So here's U1 being defined as V1, and then here's U2 being defined as V2 minus the parallel component of U1. Okay, so the inner product minus, or sorry, the inner product of U1 and V2 divided by the inner product or the norm of U1 times the direction of U1. So we're subtracting those components off, and that produces then this vector here, U2. So there's U1 and there's U2, which is what we're looking for. So you have negative 3 halves, 7 halves, negative 7 halves, and 3 halves, which is what we should have. Okay, and then U3 here is going to be V3 minus the inner product of U1 and V3 divided by the inner product of U1 and U1 times U1, the inner product of U2 and V3 times the, or divided by the norm, that's it, times, divided by the norm of U2 times U2. Okay, so that's just like what I wrote down. I'm just calculating those out, and that gives us the vector negative 42 over 29, negative 18 over 29, 18 over 29, and 42 over 29. And finally, then our U4 vector is the using V4. We're subtracting off each of the U parallel components as we expected. Okay. And now to check that our set is truly orthogonal, we look at the dot product of each of them, well, the inner product really. So here's the dot product of U1 and U2, U1 and U3, U1 and U4. Okay, the next set is U2 and U3, and then U2 and U4. The only one we haven't checked is U3, U4, and as you can see, the output for each of those is 0. So we do have, in fact, then an orthogonal set of matrices of vectors that span the space of R4. All right, I hope that was helpful, and I will see you in the next video.